pretty much a continuation of what we started last week with the 3 pillars of quality. So you need your analytical process to be good to start with. You need a QC process that's verified to detect clinically significant change. And you need staff who are going to make the right interpretation and take the right action. We're going to work with a live QC simulator. We're going to work with a real sodium example. Then we're going to make and discuss cumulative changes. There are 4 numbers that drive the analytical quality and 3 personal decisions that determine your QC effectiveness. That's all there is to quality control. 4 numbers, 3 decisions, you've got it. There are 4 key numbers, and these drive the analytical process quality. That's your measured mean, your measured SD, the true value for the sample, and the allowable error limits. We're going to cover where they come from, why they might be wrong, and we're going to link each change that we make to analytical quality and QC effectiveness. Then we're going to get into the 3 personal decisions. So where do you assign the mean? Where do you assign the SD? What QC rule do you want to use? We'll talk about how to make the right decisions and when is it right to change your QC design. So just to recap for those who weren't with us last week, we did a survey and we asked people to look at different QC charts. So we had 1 sample from 1 method. There was 1 truth, but we showed them 2 different types of QC charts with different assigned values for the mean and SD, and we had 50+ people answer the survey. So there was the same method performance, but different charts. And we asked them what they thought of this performance before the red line. Did it show acceptable precision, positive bias, negative bias, etc.? So remember, the data set is exactly the same. The only thing that's different here is where we assign the values on the QC chart. Looking at this chart, the way the lab designed it, everybody thought, or most people thought, there was a negative bias, and very few realized a chart cannot possibly show you what the bias is, and we're going to examine that more with the simulator. When we made the chart different, when we made the chart correctly, this is exactly the same data, but just those decisions as to where you want the mean and SD on the QC chart led people to a completely different interpretation. So you've got one person there going through a bunch of QC charts. Their lab decided to make the chart up this way, and they're going through saying, oh boy, I got a negative bias, maybe I should look into this. The guys over here saying, gee, I got a positive bias, maybe I should look into this. And they're looking at data from exactly the same instrument. So then we asked them, so that was what would you think? The next part of the equation is what would you do? So after the red line, what would you do? Keep reporting, stop after 1 run, stop after 2 to 5, more than 5, pause now but investigate later, and so on. So here, and we did this survey last week, we're not going to do it again, but when would you stop? That's a 1-2S warning. I ignore it or maybe report it. That one's in. There's a 1-3S, so it might take you 3 runs to stop, whereas here, just about every result is flagged. The curious thing is that here, and these both, by the way, were clinically significant changes. Both of these changes would cause the method to report more than 5% clinically misleading lab results, results that exceed your allowable error limit. When this clinically significant error occurred, even with a properly made chart and virtually every result flagged, 60% of the people stopped in the first run. Not everybody would stop with a shift of 5 SDs and every result flagged. When the chart was made incorrectly as the lab had made it, then fewer of them stopped, and it would take longer for people to stop. The longer it takes you to stop, the more patient results you're going to send out, and the the more people are going to be placed at risk, the greater the expenses are, and the clinical significance is shocking. Okay, now it's time to see what you think, because this was an interesting thing we discovered in the poll. I'm going to put up the poll twice. We're going to look first at albumin and then at sodium. And what I want you to answer is just before the change at the red line. So for the data that you see, what do you think for the albumin? And then we'll go back for the sodium. So if you want to sort of, if it's that difficult a decision, jot your answers down. And let me see if I can launch the poll. So we're asking, what would you think? And the poll is open. So 20% said the chart does, it's acceptable precision and accuracy. Another 80% said that the chart does not convey the answer, which is absolutely the right answer. Now, this may seem redundant to you, but I am going to launch the same poll again for the sodium. Does it look different to you? Does it look the same to you? Would you reach the same decisions? You cheated. I just gave you the answer. Absolutely right. So here's what the people in the poll said. A lot of them looked at this chart, the albumin, and thought it had a positive bias. But when they looked at the sodium, and I wish you guys had answered more about what you thought it did instead of just it doesn't convey the answer. I should have taken that one out of there. But nobody thought it had a positive bias. Those data sets were absolutely identical as far as their means and SDs go. The only difference is where we drew the line on the QC chart. So the lines on the chart influence staff interpretation. Where you decide to put the mean in SD influences staff interpretation. Where you decide to draw the lines influences staff interpretation. This chart is made absolutely correctly. The sodium chart, it has the real mean at the center, the real SD. This is actually at 2 standard deviations. So this shows typical expected distribution. You have 95% of the results within plus or minus 2 SD. When people looked at this chart, most of them thought it had a problem with precision. When people looked at this chart using a 1-3.5S rule, they didn't think it had a problem with precision. For some unknown reason, they thought this showed a bias. This perplexes me. I'd like to open the panel to the panel discussion to our panelists is what I'm trying to say, and see, I know we looked at this last week, but see if they've had any amazing thoughts since then as why would that happen? Okay, Anna?
Well, hello, how are you?
Good, thanks.
One of the things that I see when I look at the sodium chart to make it difficult to read is when I see the red boxes on the sodium chart, I'm assuming that that is indicating a greater than 3 standard deviation. So if I was seeing frequent areas where I'm seeing a lot of points further from the mean than what I'm anticipating, then I can begin to understand how people are saying there might be a problem with precision here because of these 3 SDs as opposed to, say, 2 SDs.
Oh.
So maybe it's the part about how the chart is read and understanding and interpreting the chart. The other thing I'd like to add, though, is one of the things that we need to be very clear about is the mean that is assigned to the chart is not the true value for the specimen. A lot of people assume that the mean that's assigned to the chart is actually the true value, and therefore that's how we can determine bias. But the mean assigned to the chart is actually our past history. So when there's a stable population, it produces a Gaussian distribution. and we can compare, the result that we obtain today based on our past history. And it's the values put on the chart that we assign that should represent our past history. So we also have problems if we don't represent our past history and begin assigning numbers to the chart that neither reflect our current Gaussian curve in a Levy-Jennings format or other reasons that we would assign numbers.
Yeah. Thanks, Anna. I just want to clarify, though, for this chart, both of these are made with the real mean at the center, the real SD assigned. Now, I see your point about the plus 3 SDs, but in actual fact, these are your 2 SD limits, and the 2 SD limits are the same on each chart. So with these charts, the mean is exactly at the center. 95% of the points on both charts fall within plus or minus 2 SD. I can understand why people make a mistake on one chart. And what I thought was curious is they seem to be taking those lines into effect when they're deciding what they're thinking about this. I didn't expect them to look at the same data and come up with a different conclusion. So I guess the point is that quality control should not be an optical illusion. People are looking at exactly the same chart, and they're making totally different decisions. And that, Mike, you're the one, and welcome, I'm glad you're here with us again today. Can you add something on to like the clinical implications if people look at the chart, not so much in this one, but if they don't stop, if they go on for 5 runs, or like 40% of them said they would not stop with that significant error, what's going to happen to their patients?
The problem is that actually, go back to the circle that says, thanks. The problem is that the clinician doesn't have the opportunity or the of looking at the Levy-Jennings, and probably doesn't even know what a Levy-Jennings is. The only thing that the clinician has is a number on a computer printout, and he makes the assumption, as do all the patients, that that's a right value. And the reality is, as was just mentioned before, that isn't necessarily a right value because it doesn't even contain any element of uncertainty measurement in it. So but the result, and so if he sees a number and he gets it repeated again in the same range, he's just going to make the assumption that while there may not be a clinical change that happens with it, that these are true values, and he may require, or she may require, make a decision to make treatment changes. And then you get into the problem, and you're spending a lot of time, effort, energy, and money trying to fix a problem that not only doesn't exist, but one which you compound into a new problem. And so if a laboratory produces a result and sees something is off and chooses to do nothing about it, it's as if the laboratory doesn't understand that the product that they're producing is the lab result. It's information, and it's information that people are going to be acting on. It's kind of irresponsible to see a big change and not stop.
Thank you, and I really like that word irresponsible, because the other thing we've done for so many years is just assume our quality control is working. And yet, you know, we never validate it. We validate so many other things. We don't validate that the QC works, and we don't, like, everybody thinks it's okay just to pick and choose. This is 192 ways to do quality control. And this is from a survey we conducted. We said to people, where do you get the mean that you put on your QC chart? And they chose all these different sources. Where do you get the assigned SD you put on your QC chart, and what rules do you use? There is exactly one recommendation for where to get your mean, where to get your SD, and what rules to use. We had 192. How do we get into this state when what people are doing is not referenced, it's not what's regulated, it's not verified to work, and it's just like quality control has slipped through the cracks somehow. We're so focused on the statistics that nobody's, like I said the other day, we're down there counting the veins on the leaves and nobody's up looking at the health of the forest. We need to back up a little bit.